Right now, you're soaring through space at an incredible 560,000 mph on a massive cosmic carnival ride where even light takes 100,000 years just to travel from one side to the other. This colossal spinning island of 400 billion stars is what we call home, our Milky Way. But here's the kicker. We've never actually seen it from the outside. We've never taken a step back to grasp its full size. Tonight, we're heading to the fringes of our space neighborhood to realize that everything we thought we understood about size and distance is just scratching the surface. If you're into this cosmic trek, tap that like button and join the ride. Get ready. Here we go. Astronauts often share how awestruck they are the first time they see Earth from above. Peering out from the tiny spacecraft window, they hunt for any known landmarks. Those massive cities turn out to be just little clusters of lights. Huge mountain ranges they once drove hours across now lay stretched out like crumpled paper. They squint down at the scene below, eager to find their town, their street, maybe even spot their very own backyard. The most startling realization, they can't see their house. They can't see any houses. From just 250 miles above, individual buildings vanish completely. Human eyesight simply doesn't capture details that small from that height. This underscores a profound truth about scale that we often overlook. Distance blurs detail. From the view on the International Space Station, entire neighborhoods fade away. Cities morph into fuzzy spots, and countries blend into hazy, green-brown smears on the globe's surface. What's massive from the ground level shows up incredibly small from space. Now, imagine pulling even further back. At 1,000 miles up, entire states morph into barely recognizable blobs. Zoom out to 10,000 miles, and continents merge, forming a blue marble suspended in the darkness. That once endless Earth you strolled across in your backyard now neatly fits within your view. But this perspective magic isn't one-sided. As we shrink when looked at from above, the vastness around us becomes more immense than our minds can handle. That empty blackness enveloping our tiny planet stretches infinitely in all directions, making Earth's width seem like a mere grain on a limitless beachfront. Think about this. If you could magically shrink Earth to the size of a marble on your desk, the closest star would still lie over 4,000 miles away. That marble would find itself lonely, surrounded by a desolate space just as vast as the stretch from New York to Los Angeles. The scale of emptiness is staggering. This overwhelming void between celestial bodies shapes our cosmic locale. We float on a minuscule rock wrapped in an ocean of nothingness so immense that light, zooming at 670 million mph, needs years to move from one celestial attraction to another. Yet, we're not entirely alone in this abyss. We're travelers on something far more colossal than a single planet, a gathering of stars and worlds so vast it defies incredible imagination. We are part of a galaxy. But here's the twist. Just as astronauts can't spot their own houses from orbit, we grapple with an even weirder challenge in trying to comprehend our galactic residence. The light photons that illuminate this page began their journey in a way that makes every human expedition seem like a mere neighborhood stroll. Light from our nearest star friend, Proxima Centauri, set off over 4 years ago. That's 4 whole years. The light now reaching your eyes began its trip when different people had different jobs, when different tunes played on the radio, and the world looked drastically different from today. This light has traveled through the vast nothingness of space for 4 years to reach you right now. When Columbus ventured about 4,000 miles from Spain to the Americas, it was perceived as an immense distance during his time. People feared he might fall off the planet's edge, worried about mythical sea creatures and endless tempests. Back then, 4,000 miles marked the outer boundary of human boldness and wonder. The light filling your room has covered 25 trillion miles. Let that sink in for a moment. 25 trillion miles. If you could drive a car at highway speeds non-stop, without ever pausing for gas, food, or rest, it would take over 40 million years to cover that length. That's 40 million uninterrupted years of driving just to meet our nearest star neighbor. It really puts the immense scale of our galactic setting into perspective. Stars that seem like tiny dots in our night sky are actually massive, fiery giants, with many being bigger and brighter than our own sun. They only appear small because they're incredibly far away. The space between them is so vast that even light, the fastest thing there is, takes years to travel from one star to another. Our galaxy is home to around 400 billion of these distant stars. While some stars, like Proxima Centauri, are just 4 light-years away, others are 50,000 light-years from us. Each star is constantly sending out photons, with their light cruising through space to reach us. Some of this starlight started its journey long before humans even existed, and some was shining when dinosaurs roamed the Earth. Looking up at the night sky is like peering into a time machine, seeing the universe's past stories being told across space. The stars we see may have actually exploded ages ago, yet their light continues to travel towards us, carrying echoes of a universe that's already changed. This sets up a curious scenario. We reside within something so immense, we'll never view it all at once. It's like being tiny creatures trying to explore a colossal clock, able to see only small parts at a time, never witnessing the entire design. Light from the galaxy's far side has spent 100,000 years reaching us, bringing news from such distant realms they might as well belong to another universe. Picture a single grain of sand resting between your fingers. Feel how light it is and how lightly it touches your skin. This little grain is about 1 millimeter across, small enough to vanish into the carpet or be scattered with a soft puff of air. It stands for one of the smallest things you can easily handle. Now imagine that grain of sand is the whole Earth. Every mountain, ocean, city, and person who ever lived is squeezed into this minute speck. The entire world shrinks to something you might accidentally inhale. On this scale, how big is your city? Your neighborhood becomes invisible. Your house vanishes. And even major cities like New York become just tiny bumps on the sand surface, needing a strong microscope to spot them. But this exercise just begins here. If Earth shrinks down to a sand grain, then the moon transforms into a small pebble floating 20 feet away. The sun becomes a beach ball half a mile further down the road. Jupiter turns into a large marble about 3 miles from where you're standing. These spans go beyond usual human experience. Half a mile still walkable, but 3 miles would take effort. Yet the closest star, Proxima Centauri, is now 125,000 miles away. You couldn't make it there by driving or flying commercially. A spacecraft would be necessary for such a journey in this sand grain universe. This scaled-down model highlights something astonishing about the universe. The distances between planets in our solar system, already mind-boggling, are practically nothing compared to the stretches of interstellar space. We share a snug spot in a warm, matter-filled pocket, surrounded by an immeasurable void. On this scale, our solar system fits within a 10-meter circle, while the next solar system lies 125,000 miles away. The emptiness between star systems is 12,000 times wider than the entire span of our local planets. But even these mind-bending distances are tiny against the full scale of our galaxy. If we persist with the sand grain perspective, our galaxy spans 11 billion miles from one edge to the other. Light, traveling at an astonishing 670 million miles per hour, would need 16 hours to cover that distance. But even this doesn't capture how truly bizarre galactic size is, because we've only considered distance so far. Right at this moment, as you read these words, you're moving faster than any human has ever moved. You're not just twirling with Earth's rotation, which spins you eastward at about 1,000 miles per hour. Nor are you simply orbiting the Sun with Earth, an additional 67,000 miles per hour added to your speed. You're actually part of something way more epic and intense than just the usual movements, you know? Our whole solar system is zooming through space at a jaw-dropping speed of 560,000 km/h. That's way beyond what we can wrap our heads around. The fastest jets only hit about 1,500 km/h. The supersonic Concorde used to cruise at around 1,350 km/h, and space rockets might get up to 25,000 km/h when they're breaking free from Earth's pull. But here we are, just chilling in our seats, racing through the universe at speeds that make these human machines seem like they're just taking a leisurely walk. What's pushing us along at such crazy speeds? Well, we're in orbit around something big. Our sun, with all its planets, moons, asteroids, and comets, is wheeling around a gravitational center that's about 26,000 light years away from us. Imagine a stone spinning on a string, except this string stretches across a distance that would take light 26,000 years to cross. This gigantic path is so huge, it takes our solar system 250 million years to complete just one loop. The last time we were in this spot, dinosaurs weren't even around yet, and the supercontinent Pangaea was just starting to form. Life on Earth was mostly simple sea creatures then. We've done just under 20 laps around this cosmic track since Earth was born. Our planet's been around for about 4.5 billion years, but in all that time, we've only made 18 full spins around our galaxy. So you could say Earth is 18 galactic years old. This really puts our existence into context. All of human history, from the first tools to space travel, happened in less than 1% of one galactic lap. Think about it. Rome rose and fell. Civilizations came and went. Entire species evolved and disappeared, all while we've been gliding through just a sliver of our cosmic area. But what's at the center of this massive orbit that has enough gravity to pull our solar system and countless other stars along for the ride? The answer involves something so extreme, it actually bends space itself. For the longest time, humans thought we were at the heart of everything. We imagined the Earth sat still while the sun, moon, planets, and stars danced circles around us. It's understandable since we couldn't feel any movement at all. We saw celestial bodies rise and set like clockwork, a perfect system that seemed to confirm we were sitting pretty at the universe's center. This comforting belief stuck around until astronomers with better tools started making precise measurements. First, they figured out that Earth circled the sun, not the other way around. That was a blow to our ego. But hey, maybe our sun was still at the center of something bigger. But then, in 1917, astronomer Harlow Shapley made a discovery that crushed even that small comfort. Shapley looked at globular clusters, dense groups of ancient stars that hung around our galaxy like fireflies at a campfire. He checked out their distances and mapped where they were. What he found was stunning. They weren't centered around our solar system or even our local area. Instead, they were gathered around a point about 30,000 light-years away in the direction of Sagittarius. Our solar system wasn't anywhere near the center of anything. It was more like a rural outpost in the galactic suburbs, far from the main hustle. This discovery showed we're part of something far bigger than anyone had thought. Shapley realized our galaxy was about 100,000 light-years across. Our solar system sits roughly 26,000 light-years from the center, way closer to the edge than the middle. If the galaxy were a pizza, we'd be living near the crust, definitely not in the prime spot with all the best toppings in the center. As it turns out, that's actually pretty fortunate for us. The galactic center is a wild, chaotic place full of intense radiation and crazy gravitational forces, stuff that would make any nearby planets pretty inhospitable. Our peaceful suburban spot offers a perfect setting where complex chemistry has billions of years to unfold. But Shapley's discovery led to a new puzzle. What enormous entity lies 30,000 light-years away and has the gravity to hold hundreds of billions of stars in this gigantic whirl? It took decades to figure it out, and the truth turned out to be even weirder than anyone imagined. Astronomers had a tricky task to tackle. How do you gauge the size of something you're stuck inside? Figuring out the dimensions of our galaxy was like trying to measure a forest while standing among the trees or mapping a city without stepping outside its boundaries. Harlow Shapley cracked this conundrum with a smart approach. Since he couldn't step outside the galaxy for a direct measurement, he charted the positions of globular clusters, those dense, ancient star-packed balls orbiting our galaxy like distant streetlights. He realized these clusters formed a roughly spherical halo around our galaxy. By measuring distances to multiple clusters and plotting them in 3D space, Shapley could trace our galaxy's outlines, using the clusters like survey markers to define a structure invisible to the naked eye. This meant solving another challenge, calculating distances to objects tens of thousands of light-years distant. Shapley turned to Cepheid variable stars, which brighten and dim in a steady rhythm. Remarkably, the speed of their pulsing indicates their true brightness. Slower pulsing means a brighter star than fast pulsing ones. This gave Shapley a universal yardstick. By timing a Cepheid star's pulse to find out how bright it truly was, then comparing that to its apparent brightness from Earth, he could deduce the distance, since farther objects seem dimmer. Using this method, Shapley measured distances to dozens of globular clusters scattered in the sky. A pattern became clear as the clusters sketched out a vast spherical area around 100,000 light-years wide. Our solar system wasn't in the middle. Instead, it sat about 2/3 from the center to the edge. Shapley's revelation was startling, even to himself. His 100,000 light-year estimation greatly surpassed previous galaxy-size guesses, which were thought to be only a few thousand light-years, similar to distances between neighboring stars. Instead, Shapley revealed we live in something truly massive. At 100,000 light-years, light, traveling at 670 million mph, would need 100,000 years to traverse our galaxy. Shapley's measurement has mostly stood the test of time, with only slight refinements using modern techniques, yet his basic scale was spot on with tools that now seem basic. However, Shapley's globular clusters only marked the visible edges of our galaxy. An unseen, untouchable, unpredictable force surrounds us, something that outweighs all visible matter in our galaxy by about 20 to 1. Stars, planets, gas, dust, and all we can see make up just 5% of our galactic home. 95% is made up of what's called dark matter. How do we know this invisible matter is there if we can't see it directly? Just like sensing wind without seeing air, we observe its influence. Stars at our galaxy's outskirts move so fast they should zoom away into intergalactic space, like mud spinning off a tire. The gravity from all visible matter isn't enough to keep these quick-moving stars in orbit. There's got to be something else out there, something huge enough to provide the extra gravitational force needed to hold our galaxy together. This unseen mass creates a roughly spherical halo around our galaxy, reaching far beyond the visible, star-packed disk. New data shows this dark matter halo spans about 2 million light-years. That's right, 2 million light-years. So, the actual edge of our galactic neighborhood is 20 times farther than the stars we can see. Most of what makes up our galaxy is empty space filled with mysterious particles that boggle our minds. Picture it this way. If our visible galaxy was like the beam of a flashlight in a dark room, the dark matter halo would be the entire room around that light. We're inside this beam, enveloped by an immense mass that we can only detect through gravitational pull. This dark matter doesn't act like regular stuff. It doesn't emit or absorb light, and doesn't interact with electromagnetic waves at all. These particles pass right through regular matter as though it wasn't even there. Every second, billions of dark matter particles fly through your body without affecting you one bit. Scientists guess there's somewhere between 600 billion to 3,000 billion times the mass of our sun in dark matter, forming a halo around our galaxy. This unseen mass shapes our galaxy's structure and growth in ways we're just starting to figure out. Dark matter's existence poses deep questions about what reality really is. Most of the universe is made of stuff we can't see or touch or directly detect. We're in a universe where the familiar material that makes stars, planets, and us is just a tiny fraction of the whole. But even this hidden halo has its limits. And beyond those limits, there's even more to blow your mind. Back in 1977, we sent 2 robotic explorers to the outer planets, Voyager 1 and Voyager 2. They're the fastest things humans have ever launched into deep space. They zoom away from our solar system at about 38,000 bateaux par, quick enough to fly across the U.S. in under 5 minutes. They've traveled farther from Earth than anything else we have ever made, sending messages for any potential alien life and snapping amazing pictures of far-off planets. However, their phenomenal speed, achieved by using gravitational assists from several planets, is laughably slow for galaxy-wide travel. At 38,000 mph, it would take Voyager 1 about 173,000 years to reach the nearest star, if it were even aimed that way. That's 173,000 years, a time span 10 times longer than all of human history. Farming, writing, cities, empires, industry, and space travel all arose in a much shorter window than it would take to just get to our closest star. And that's just the very beginning of exploring the galaxy. Voyager needs about 1.7 billion years of continuous travel to cross our galaxy's breadth. 1.7 billion years. That's not only longer than human history, but longer than the history of complex life on Earth. When Voyager would start such a hypothetical journey, the most advanced life on Earth were basic bacteria and algae. Multicellular life, animals, and plants weren't even on the scene yet, and Earth's atmosphere, was nearly devoid of oxygen. Over the billion-plus years needed for a trip across our galaxy, life evolved from single cells to the complexity we know today. This underscores the vastness of galactic distances. Life's journey from microbes to mammalian intellects takes less time than crossing our cosmic block at the speeds we can currently achieve. But this assumes Voyager could keep speeding along forever without running out of fuel, breaking down, or hitting anything. In reality, both Voyager crafts will fall silent within the next decade as their nuclear power runs out. They'll continue drifting as silent metal and plastic relics, never to report back on the mysteries of interstellar darkness. The stretch between stars is practically a perfect vacuum. Voyager encounters fewer than 1 atom per cm3 in this immense void. This is a level of emptiness beyond anything we can replicate in labs on Earth. The spacecraft is flying through regions so devoid of matter that it might not see another solid object for millions of years. This vast emptiness is what shapes our galaxy's structure. In our galaxy, stars gather in a flat disk, but unimaginably large gaps sit between each star. Yet, our galaxy is filled with far more than just lone stars scattered across empty space. There are more stars in our galaxy than grains of sand on all of Earth's beaches. Within our cosmic home, a whopping 400 billion stars shine. That's a number so big, it blows the mind. If you tried to count them one by one at a rate of 1 star per second, day and night, it would take over 12,000 years to finish the task. If everyone on Earth took on the job of counting a small bunch of stars, each person would have to count about 50 to get through them all. These stars come in all sorts of sizes, colors, and ages. Some stars radiate a blue-white light and burn their fuel quickly, lasting just a few million years. Others glow a gentle red, using their fuel slowly and shining for hundreds of billions of years, long after our sun kicks the bucket. Some stars are just barely massive enough to keep nuclear fusion going, while others cram in dozens of times more material than our sun into their incredibly dense and hot cores. This variety is more than just differences in size and heat. Certain stars come in pairs, elegantly orbiting around each other in gravitational dances. Some gather in groups of dozens to hundreds, creating stellar neighborhoods alive with radiation and gravitational interactions that result in strange phenomena. A few stars pulse with consistent rhythms, resembling cosmic lighthouses as they cast beams across the universe. Within these 400 billion stars, at least 100 billion planets orbit within habitable zones where liquid water could potentially exist. That's 100 billion potential homes for life scattered throughout our galaxy. Some of these planets might harbor life, some might host advanced civilizations, and some might be home to intelligent beings pondering the same questions about the universe that we are now. The oldest stars in our galaxy came into being more than 13 billion years ago, back when the universe itself was still young. These ancient stars have been witnesses to the entire history of cosmic evolution, from a period when heavy elements were scarce to the present era of rocky planets and complex chemistry. Planetary systems around these old stars might have sustained life for billions of years longer than Earth has been around. This massive star population doesn't randomly distribute itself across the galaxy. Stars arrange themselves into a flattened disk about 1,000 light-years thick and 100,000 light-years wide. Our solar system is tucked within this disk, approximately 26,000 light-years from the galactic center. From this spot in the disk, we can see the collective glow of billions of distant stars when we gaze toward the galactic center. This is what creates the bright ribbon of the Milky Way that stretches across our night sky. We're viewing it edge-on, looking through the flat plane of our galaxy, taking in the combined light of countless suns too far away to distinguish on their own. However, those 400 billion stars are merely the start of our galactic inventory. Our galaxy spins around like some enormous cosmic pinwheel, but its rotation is very different from what we're used to on Earth. With a record player, for instance, the entire record revolves together, each part making a full turn in the same time span. The center and the edge sync up, holding their relative positions. But our galaxy's rotation is different. Stars situated nearer to the center whip around much faster than those on the outer edges, kind of like runners on a track, where those in the inner lanes sprint ahead of those on the outside. Our solar system, roughly 26,000 light-years from the galaxy's center, takes about 250 million years to finish a single orbit, a time frame astronomers call a cosmic year, which serves as a handy unit for measuring galactic timescales. Since Earth came into being 4.5 billion years ago, it's only managed to complete 18 trips around the galaxy, 18 cosmic years. All of Earth's history, from the first rocks to today's moment, fits into less than 20 of these giant galactic rotations. Think about how this all fits into the story of life on Earth. When our planet last completed a lap around the galaxy 250 million years ago, the massive landmass Pangaea was just splitting apart. There weren't any dinosaurs yet either. The most complex creatures were basic reptiles and amphibians, and there were no mammals or flowers or even grass. Dinosaurs ruled for about a quarter of a galactic year before vanishing 65 million years ago. Human civilization, in comparison, has been around for less than a tiny fraction, about a 110,000th of that cosmic year. If you shrunk our galaxy's history down to one Earth year, all of human existence would just be a couple of seconds before New Year's Eve. This gradual orbit has some fascinating effects on nearby stars. Close-by stars today will drift far apart over time, and constellations we know and love may look completely different in just a few million years. Our solar system follows a path that bobs up and down through the galaxy's disk as it travels around the center, spending about 33 million years above and below the plane, taking around 66 million years for a full cycle. Some scientists think this vertical dance might line up with extinction events on Earth. Crossing through the dense middle of the galaxy could disrupt outer space debris, sending comets hurtling inward. Stars move at different speeds across the galaxy, creating a complex motion called differential rotation. At the heart of our galaxy is something colossal and dense, warping space and time itself, Sagittarius A, a supermassive black hole with the heft of 4 million suns, all packed into a space smaller than our solar system. This black hole's gravity holds our galaxy together, uniting 400 billion stars into one rotating form. Its presence causes bizarre effects beyond normal understanding, where time stretches near its event horizon, running slower than here on Earth. Since light can't escape, we can't see the black hole itself, but its influence is visible on nearby stars, some racing at speeds over 3,000 km/s as they orbit this unseen center. These stars circle the black hole within years rather than in centuries or longer spans. The black hole sometimes consumes gas clouds or entire stars that wander too close, heating them to millions of degrees as they disappear forever. Observations show Sagittarius A spins nearly as fast as possible for a black hole, dragging space around it in a phenomenon predicted by Einstein's relativity theory. This black hole likely began small and grew by pulling in gas, dust, and stars over time, helping form our spiral galaxy. The core of our galaxy is chaotic, with intense radiation, magnetic forces, and gravity making it a tough spot for forming planets or life. Stars here burn bright and explode quickly, adding chaos to the already tumultuous environment. Even though we're 26,000 light-years away, we still experience this black hole's gravitational pull. At the heart of our solar system is a central point that guides our orbit, along with all the other stars in our galaxy neighborhood. However, Sagittarius A still is just one part of a much bigger, more intricate galaxy. We've got a unique challenge. No other astronomers in the universe have to deal with this. We're trying to study something we're smack in the middle of. While other galaxies can be seen from the outside, fully photographed and mapped from a safe distance, we're left to piece together our galaxy's structure from within its limits. Imagine trying to map out a massive city while stuck in a windowless basement apartment. You could ask people to check out different streets and tell you what they see, but you wouldn't ever be able to view the city from above. That's our exact dilemma. Looking towards the galaxy's center, we're staring through a flat disk filled with most of our galaxy's stars and dust. Interstellar clouds block our view like fog, making it tough to see visible light with our telescopes. We can only see a few thousand light-years through this cosmic haze before everything fades into darkness. Although radio waves and infrared light can cut through the galactic mist better than visible light, they still don't offer the clear, wide view of external galaxies that other astronomers have. Our edge-on perspective brings more trouble. Gazing along our galactic disk plane, we see a blend of light from billions of faint stars merging into the bright swath we call the Milky Way. It becomes impossible to see individual stars from far away, and we lose the sense of its three-dimensional layout. Surprisingly, this has led to some incredible discoveries. Being inside our galaxy lets us study individual stars much closer than if we were looking at other galaxies. We can precisely check out star neighborhoods, map gas clouds' chemical makeup, and find planets around nearby stars, something you couldn't dream of from outside our galaxy. Space missions are starting to tackle some of these observational hurdles. The Gaia spacecraft has recorded the exact positions and movements of over 1 billion stars, creating the most detailed 3D map of our galaxy ever made. These data patterns help us grasp our galaxy's layout and past. Still, we'll never get to leave our galaxy and snap a distant photograph of it. We have to stay inside our cosmic home, like living in a huge mansion and exploring only one room at a time, unable to see the whole picture. This limitation makes our next finding even more impressive because it's about things we can't see directly and can only detect through gravitational clues. Our galaxy's spiral arms are more like cosmic traffic jams than solid features. Many picture them as fixed, giant pinwheel arms spinning through space. But that's not right. These arms aren't full of permanent matter, but are regions where stars and gas cluster temporarily before scattering back into the galaxy's disk. Think of rush hour traffic on a busy road. Cars get stuck near construction sites or accidents, creating slow-moving clusters that seem solid from above, despite constantly changing. Cars enter and leave the jam all the time, yet the jam itself holds its shape and position. This is how our galaxy's spiral arms behave too. Individual stars orbit our galaxy's center at their own pace, sometimes passing through spiral arms similar to cars moving through traffic congestion. The arms of our galaxy are like waves of compression moving around, causing temporary gatherings of stars, gas, and dust. These waves press the gas clouds tightly, leading to intense star formation. New stars light up in bright blue clusters, highlighting the spiral arms so we can see them from afar. The biggest and brightest stars have short lifespans, exploding as supernovas before moving far from where they were born. This makes it seem like the spiral arms are full of young, luminous stars all the time. Right now, our solar system sits between two major spiral arms in a smaller segment called the Orion Arm. We last crossed a significant spiral arm about 50 million years ago and won't do so again for another 10 million years. As we move through these arms, our solar system encounters more gas, dust, and radiation, potentially impacting Earth's climate and life. The spiral structure rotates around our galaxy slower than individual star orbits, allowing stars to move in and out of these arms over time. If the arms rotated as fast as stars, they would quickly wind into tight spirals and vanish within hundreds of millions of years. Scientists still discuss what exactly forms and keeps the galaxy's spiral form. Interactions with smaller companion galaxies might add energy to the galaxy's disk, maintaining these waves over billions of years. Alternatively, the galaxy's central bar-shaped area might influence spiral patterns through complex gravitational processes. New observations show our spiral arms have a surprising complexity, with branches, spurs, and gaps shifting over tens of millions of years. However, spiral arms are merely the most visible part of something much bigger and more mysterious. Our galaxy isn't moving through the dark universe alone. Zoom out far enough, and a surprising sight appears. Small companion galaxies float around us like moths around a flame. Despite being much smaller than our collection of 400 billion stars, these satellites hold millions or even billions of their own stars. They're bound to our galaxy by gravitational forces stretching across huge distances. Two well-known companions are visible in the southern hemisphere's sky. They are the Large and Small Magellanic Clouds, which appear as patches of light resembling pieces of our Milky Way. Early ocean explorers used these features for navigation, unaware they were entire galaxies. The Large Magellanic Cloud, with about 10 billion stars, is situated 160,000 light-years away. The Small Magellanic Cloud, hosting around 3 billion stars, is slightly farther at 200,000 light-years. Both galaxies lie well beyond our visible stellar disk within our extended dark matter halo. These companion galaxies don't orbit peacefully, as our massive gravitational field pulls and stretches them. Streams of gas and stars are dragged from both Magellanic Clouds, forming lengthy trails of matter behind them as they orbit our galaxy. Yet, the Magellanic Clouds are just the largest members of a bigger family. Over 30 smaller satellite galaxies fill our local area, mostly holding a few million stars each. These are named after the constellations they appear in, like Draco, Sculptor, and Fornax. Many are so faint we only spotted them recently using advanced devices to detect their dim light against starry backgrounds. Some hardly contain any regular matter and are mostly made up of dark matter, making them incredibly hard to detect despite having the mass of millions of suns. Over cosmic time, Our gravitational pull takes a heavy toll on these companions. As they loop around our extended halo, some invisible force nibbles away their outer stars, adding to our galaxy's mass. We're slowly consuming our smaller cosmic neighbors, getting bigger at their expense. And this has been going on for billions of years. This act of galactic cannibalism gives us a peek into how massive galaxies like ours form and evolve over time. The galaxy you see is just the bright center of something much larger and almost completely hidden. Recent observations show our dark matter halo stretches nearly 2 million light-years from our galaxy's core. That's 20 times further than the visible edge of our starry disk. Most of our galaxy is made up of empty space filled with unseen matter, detectable only by its gravitational influence. Picture our visible galaxy as a cherry pit nestled at the center of a basketball. The pit stands for the 100,000 light-year disk where all our known stars, gas, and dust reside. Meanwhile, the basketball symbolizes the full range of our galactic reach, filled with dark matter that only interacts gravitationally. This invisible halo holds at least 10 times the mass of all visible stars and gas combined. We're surrounded by 600 billion to 3 trillion solar masses worth of dark matter, forming a vast, roughly spherical cloud that overshadows everything we can actually see. We're like deep-sea creatures, living in a lit zone of an ocean that stretches far beyond our comprehension. The dark matter halo influences everything within its boundaries. Satellite galaxies drift through this unseen medium, feeling gravitational forces from matter they can't perceive. The paths these companion galaxies take reveal the true gravitational map of our cosmic domain, hinting at dark matter through their movements. Recent simulations suggest our dark matter halo is dotted with thousands of smaller subhalos. These are dense clusters of invisible matter moving through the larger body like schools of fish gliding through the sea. Some of these subhalos might gather enough ordinary matter to create small satellite galaxies, while others stay eternally dark, made up only of particles that never interact with light. The halo's influence not only ties our galaxy to the wider universe, but it also draws in gas from intergalactic space, fueling new star creation. Simultaneously, it shields us from cosmic havoc, deflecting high-speed particles and small objects that could damage our galaxy's delicate structure. The line between our dark matter halo and intergalactic space is hazy. The halo's density gradually fades as it stretches out from our galactic core, eventually becoming too thin to discern and blending seamlessly with the general dark matter that fills the universe. But this gigantic invisible halo is just one piece of an even larger cosmic puzzle. Our galaxy isn't the stable, perfectly balanced disk many imagine. Instead, it wobbles and bends like a spinning coin, slowly losing speed. The outer edges of our galactic disk twist up and down, creating ripples that move inward towards the center like waves in a disturbed pond. This twisting motion is one of the most surprising aspects of our galactic structure. Observations using stars of different ages have uncovered that our galaxy's warp slowly rotates backward at about 1,200th of a degree every million years, meaning the warp pattern itself gradually moves around our galactic center opposite to our star's orbital path. What causes this odd wobbling? The likely culprit is our dark matter halo. Computer models suggest our invisible halo has a slightly squished shape, like a football, not a perfect sphere. As our stellar disk spins within this oblate dark matter structure, gravitational forces create the wobbly motion we see, much like a coin wobbling on a tabletop. As the coin spins, friction causes it to start wobbling more and more until it finally falls flat. The same sort of thing happens with our galaxy, but here it's not friction. Instead, it's the way our spinning disk doesn't quite line up with the main axis of our dark matter halo that fuels this wobbling dance. This shakes things up for everything in our cosmic backyard. Stars way out in the outer areas of our disk get jostled around by the waves. Gas clouds get squeezed and pulled as the disk bends around them. Even our solar system, pretty close to the galaxy's middle, gets caught up in this slow-moving rhythm. This wobble also spills some of the beans on dark matter's spread around our galaxy. By keeping track of how the warp shifts around, astronomers can figure out the shape and path of that invisible halo that makes up most of our galactic mass. It's one of the rare ways we can get clues about dark matter on such a big scale. Our galactic neighbors add even more twists to this wobble story. The large and small Magellanic Clouds and other smaller galaxy pals put their own gravitational 2 cents in on how our galaxy's structure looks. Their orbits add extra twists that adjust the speed and path of our galaxy's wobble. This all shows that our galaxy never stays put, always adapting to the gravitational pushes and pulls from things we can see and can't see. But there's an even bigger change on the horizon for our wobbling disk. Around 4.5 billion years down the line, our night sky will get a dramatic makeover from one of the universe's most jaw-dropping events, the Andromeda Galaxy. Our closest big galactic neighbor is zooming towards us at a staggering 250,000 mph. When it finally collides with our galaxy in what experts call a surefire cosmic smash-up, it will completely transform both galaxies beyond recognition, fashioning a new cosmic structure from the remnants of our old homes. For now, Andromeda is just a faint, misty patch of light in our autumn skies, tough to spot with the naked eye, even though it has more stars than our galaxy. This seemingly delicate spiral is just 2.5 million light-years away, making it our closest big galaxy neighbor, sharing the cosmic neighborhood. As Andromeda draws near, its gravitational tug will start to mess with our galaxy's layout long before the big bump happens. Our far-off spiral arms will stretch and twist. Streams of stars will peel off from both galaxies, forming vast bridges of matter spanning the distance between these massive entities. The actual crash will take place over billions of years, like a slow-motion calamity stretching over timescales we can't even imagine. Despite the trillion-plus stars between them, actual star collisions will be super rare because each is so far apart. The crash will be more like clouds of fireflies passing through, with gravitation reshuffling their paths. Our sun will probably survive the merger, though exactly what happens to it isn't clear. Simulations suggest our solar system might get flung to the outer edges of the new galaxy or even booted into space between galaxies. Earth might end up circling a lone star with no galaxy to belong to. The supermassive black holes from both galaxies will slowly merge, joining forces into a single massive beast with over 5 million solar mass. This final black hole smash-up will churn out more gravitational energy than our sun will ever release in light. The new galaxy formed, dubbed Milky-Way, won't look like either of its parents. Instead of graceful spirals, we'll see a rough elliptical galaxy, a more random mass of stars with no spiral arms to speak of. Yet this smash-up is just a sample of the wild cosmic environment swirling around us. Our entire local group of galaxies, which includes both the Milky Way and Andromeda, is speeding toward something big and puzzling at 600 meters per second. This sums up our shared speed toward a gravitational hotspot that astronomers refer to as the Great Attractor. This unseen mass concentration is around 150 million light-years away, pointing toward the constellations Hydra and Centaurus. It hides behind the dust and stars of our galaxy's disk, but still manages to tug on thousands of galaxies over hundreds of millions of light-years. Its pull is so strong it affects the movement of our entire cosmic neighborhood, pulling galaxy clusters and superclusters toward it. Much like debris trapped in a cosmic vortex, this monster is enormous enough to control gravity over vast spaces. The Great Attractor contains mass equal to tens of thousands of galaxies like ours, crammed into an area about 500 million light-years wide. This makes it one of the biggest structures we've discovered in the universe. It acts like a gravitational anchor, guiding the flow of matter over immense cosmic distances. The plot thickens, though, because the Great Attractor is partially obscured by our own galaxy. When we peek in that direction, stars and dust from our galaxy's disk block our view of what's beyond. Astronomers call this area the zone of avoidance, since it's tough to observe anything thanks to our own cosmic surroundings. But with telescopes capable of seeing through the dust, astronomers have pinpointed several hefty galaxy clusters near the Great Attractor's direction. The Norma cluster, the Centaurus cluster, and the Hydrus cluster all add to the gravitational pull that influences how we move through space. Yet, tallying up all these observable structures still doesn't account for the entire pull we detect. There's got to be something else out there. Additional mass, maybe in the form of dark matter arrays or hidden galaxy clusters, adds to the Great Attractor's gravitational clout. The full list of stuff responsible for pushing our galaxy through space remains a mystery, hidden behind our own galaxy's dust. This discovery shows our galaxy doesn't just wander through space. Instead, we follow gravitational paths set by the universe's largest structures. We're like passengers riding along a cosmic river, moved by forces too big for even our massive galaxy to ignore. Recent studies uncovered an even larger structure beyond the Great Attractor. The Shapley supercluster, with its thousands of galaxies, might be where we're headed on this cosmic journey. Yet, the gravitational story in our cosmic neighborhood isn't just about distant attractors. Our galaxy acts like a cosmic predator, gradually consuming smaller neighbors that drift too close. The Sagittarius dwarf elliptical galaxy is a perfect example of this cosmic cannibalism. This small cluster of about 4 billion stars is passing through our galaxy's disk and gets torn apart by our gravity as it tries to orbit around our galaxy's center. Over the last few billion years, our gravity has gradually stripped most original stars from the Sagittarius dwarf. Now long streams of stars trail behind the disrupted galaxy like ribbons, tracing its orbit through our galactic halo. These stellar streams wind all the way around our galaxy, forming rings that move along with their parent galaxy's movement. This destruction happens slowly but surely. Each time the Sagittarius dwarf crosses our dense galactic disk, tidal forces pull off its outer stars. The dwarf galaxy shrinks with every pass, losing mass and slowly blending into our larger star community. Computer models predict that in the next few billion years, the Sagittarius dwarf will completely vanish, its stars absorbed into our galaxy's structure. This act of galactic cannibalism has been part of our galaxy's growth for billions of years. Many stars in our galactic halo were likely born in small satellite galaxies, captured and consumed over the past 10 billion years by our galaxy's gravity. The stars sprinkled around our galaxy's halo are actually the remnants of many smaller galaxies that got merged together. The Large Magellanic Cloud is headed for a similar end, although its demise will take way longer. Recent findings about its movement indicate it might not be circling our galaxy steadily. Instead, it could be making its initial close encounter with us, drawn in by our galaxy's gravitational pull. As it spirals closer over the coming billions of years, our galaxy's gravity will slowly pull away its outer stars and gas. As this happens, its gas will mix into our spiral arms, sparking new bursts of star formation in our galaxy. Even the tiniest satellite galaxies orbiting us show signs of this slow destruction. These ultra-faint dwarf galaxies with only a few thousand stars display evidence of being torn apart by tidal forces. Their stretched-out shapes and scattered stars reveal the gravitational turmoil they faced in their journeys through our galactic space. This process of galactic consumption is a key part of cosmic evolution. Big galaxies like ours mainly grow by swallowing up smaller neighbors, rather than by gathering material from the vast intergalactic reaches. Clues of this cosmic feasting are all around us, etched in the movements and layouts of stars across our galaxy. For years, astronomers debated if our galaxy had a feature that's pretty common in spiral galaxies elsewhere in the universe. Most spiral galaxies have a central bar, a long stretch of stars sticking out from the center like the handle of a cosmic dumbbell. These bars are crucial for galactic growth as they help funnel gas inward to spark star birth and shape the spiral arms that give galaxies their iconic look. But figuring out if our galaxy had such a bar was tough. Being inside the galaxy, understanding its big picture structure is like trying to map a forest while standing deep among the trees. Dust clouds scattered throughout our galaxy block visible light, creating a big barrier that stops us from seeing the center and makes it hard to puzzle out the structure. The breakthrough came in 2005 with the Spitzer Space Telescope using infrared light to finally peek past the dust and chart the star layout in our galaxy's center. Infrared light passes through cosmic dust much better than visible light, letting astronomers finally see the part of the galaxy that had been hidden from view. The infrared data uncovered something stunning. Our galaxy does have a central bar, reaching about 27,000 light-years from one end to the other. This gigantic star structure rotates like a single unit around our galactic center. This insight solved several mysteries about our galactic behavior. The central bar helps shape our spiral arm by stirring up gravitational disturbances that make gas clouds squeeze together as they move through the galaxy. It also directs material toward our central supermassive black hole, fueling it for occasional feeding sprees. Our galaxy's bar spins faster than the solar system does, making a full turn every few 100 million years. This means various parts of our galaxy align with the bar's gravity now and then, triggering star formation waves through our spiral arms. The presence of the bar also influences our galaxy's future development. As it spins, the bar gradually sheds angular momentum to the surrounding disk, causing it to lengthen and become more pronounced over time. Computer models suggest our bar formed relatively recently, within the last few billion years. This discovery changed how we see our galaxy's structure. Rather than just a simple spiral setup with a round central bulge, we live in a barred spiral galaxy with a complex inside that drives much of the activity we observe around us. The bar is just a piece of the puzzle in our galaxy's surprisingly intricate and lively interior. Across its vast reaches, about 3 stars are born each year, while 2 end their journey. This stellar life cycle has been going on for over 10 billion years, slowly transforming the original hydrogen and helium into the heavier elements that create rocky planets and support life. Every atom in your body except hydrogen was formed in the nuclear cores of massive stars that lived, died, and spread their remnants into space. Star creation doesn't happen randomly in our galaxy. It's mostly found in the spiral arms, where waves compress gas clouds into denser forms. These pockets, filled with newborn stars, shine brightly, creating the vivid patterns seen in spiral galaxies across billions of light years. The biggest stars, with 10 to 100 times more mass than our Sun, burn out in a few million years and end with explosive supernovas. These blasts unleash more energy in mere seconds than our Sun will in its entire 10 billion year lifespan. Supernova shockwaves compress nearby gas, kicking off new star formation in a never-ending cycle. Smaller stars like our Sun fuel themselves much slower, shining for billions of years before ballooning into red giants and finally shrinking into white dwarfs. These enduring stars offer stable energy, potentially nurturing the evolution of life on orbiting planets over immense timescales. The makeup of new stars has shifted drastically throughout our galaxy's history. The first stars sprang from pure hydrogen and helium, the sole elements post-Big Bang. As these first stars ended, they scattered heavier elements in space via winds and supernovae. Each new star generation absorbed these elements, enriching our galaxy with carbon, oxygen, silicon, iron, and other essentials for complex chemistry. Our Sun, forming roughly 4.5 billion years ago, is at least a third-generation star created from this recycled material. Currently, our galaxy's star production rate has dropped from its peak around 10 billion years back. In its younger days, the galaxy birthed stars at 10 times today's rate. This slowdown is due to the steady depletion of materials needed for star making as more gas gets trapped in long-lived stellar remnants. Computer models indicate our galaxy will keep generating stars for billions more years, though at a slower rate. Star formation will eventually halt when gas and dust run out. This stellar recycling touches our entire galactic home. The galaxy's boundary is more expansive than previously thought. Many astronomers believed our galaxy's disk ended around 50,000 light-years from the center, with little beyond except a few clusters or stray stars. But new observations have challenged this idea. In 2018, astronomers using Gaia mission data found disk stars from 84,000 to 103,000 light-years away. These far-off stars extend the galaxy's known limits by tens of thousands of light-years, beyond what was once considered its edge. Further studies have pushed this boundary to nearly 130,000 light-years from the center, meaning the galaxy stretches much farther than its long-held 100,000 light-year diameter. And that's just part of the picture. Recent measurements suggest our galaxy's dark matter halo might reach nearly 2 million light-years, stretching 20 times beyond the visible stars. Our galaxy's real border extends almost halfway to the Andromeda galaxy, which is our closest larger neighbor. This vast reach poses a mystery for understanding how galaxies form and evolve. How does our galaxy keep stars in an organized manner so far from its central gravitational pull? Out in these distant regions, stars take over 1 billion years to complete an orbit, meaning they've only orbited a few times since the galaxy's birth. This discovery also makes us wonder where exactly our galaxy ends and intergalactic space starts. If our dark matter halo spans 2 million light-years and Andromeda's halo is similar, they might already be touching or overlapping. So, in a way, the collision between our galaxies might have already started, even though our stars won't mix for another 4 billion years. Interactions with smaller galaxy satellites might shed light on these far-flung stars. As we pull apart nearby small galaxies with our gravity, their stars disperse across vast distances. These scattered stars could explain the remote stars found in our galaxy's outskirts. As we keep expanding our understanding of the galaxy, that's thanks to better observational tools and data analysis. New telescope generations and space missions continue to uncover hidden parts of our universe, extending what we know ever further. This trend hints that our galaxy could be even bigger than current estimates suggest. There's also an invisible network of magnetic highways stretching across our galaxy, moving charged particles over distances bigger than whole solar systems. These magnetic fields, though much weaker than a fridge magnet, span the 100,000 light-years of our galactic space. They're like cosmic power lines, shaping the flow of charged gas and affecting star formation and death across our galactic area. These magnetic lines follow the galaxy's spiral pattern, wrapping in huge arcs around the center, much like the spiral arms. This happens because the galaxy's rotation twists the magnetic field, similar to how twisting a wet towel lines up the water spirals. These invisible magnetic paths are key players in galactic dynamics, even though we don't notice them in daily life. Charged particles such as cosmic rays from supernovae travel along these lines, sometimes moving thousands of light-years before finding something to change their course. Magnetic fields also play a role in star formation by supporting pressure to counteract gravitational collapse in gas clouds. When these magnetic lines tangle or compress, they can either help or hinder new stars forming, depending on local conditions. This magnetic balancing act helps clarify why star formation flourishes in some galaxy areas while others stay sparse. Recent space missions have started mapping these magnetic structures in our galaxy with incredible detail. The European Space Agency's Planck mission, for instance, observed how interstellar dust grains align with local magnetic fields by studying polarization in light. These observations revealed intricate webs of magnetic structures weaving through the galaxy's disk. Our galaxy's magnetic fields come from the movement of electrically charged gas. Clouds of ionized hydrogen drifting through space create electric currents that generate these fields. The galaxy's rotation then strengthens and organizes them into the large-scale patterns we see now. The magnetic field strength varies wildly across different regions. Near the galactic center, intense star activity and the supermassive black hole boost magnetic strength hundreds of times above the average. In the quieter zones between the spiral arms, the magnetic fields aren't strong enough to have much effect on charged particles. When magnetic lines break and reconnect in new ways, these reconnection events unleash huge bursts of energy over vast interstellar distances. Such magnetic phenomena tie our galaxy's structure to the wider electromagnetic tapestry of the universe. Our galaxy is really just an average part of an almost ridiculously large cosmic population. Recent guesses reckon there are about 2 trillion galaxies in the observable universe, each brimming with stars, gas, and dark matter. 2 trillion. That figure blows past previous guesses by a long shot, uncovering the universe's hidden abundance of these galactic cities that no one had anticipated. Our Milky Way. It's less than a single trillionth of all those galaxies. Among this massive crowd, our galaxy isn't particularly special. With around 400 billion stars, we're smack in the middle when it comes to galactic mass. Sure, some galaxies have fewer stars, but others absolutely outsize us. Take the biggest elliptical galaxies. They pack in more than 1 trillion stars, making our galactic home seem tiny. Structurally, our galaxy is also pretty standard for spiral galaxies everywhere. About 60% of all galaxies show off spiral shapes like ours, with central bulges, flat disks, and standout spiral arms. We're part of one of the most common cosmic designs, mirroring billions of other spirals scattered through space. Yet, our galaxy does have a few quirks that make it stand out from the typical cosmic lineup. We find ourselves in a pretty calm galaxy neighborhood, far from the busy galaxy clusters, where things often get chaotic with cosmic collisions and mergers. Most galaxies hang out in busier spots, where gravity often stirs up galactic structures. Our galaxy is also unusually on its own compared to most spirals. Yes, we have our satellite galaxies and are set to dance with Andromeda eventually, but many spiral galaxies call tighter groups or clusters home, where multiple large galaxies gravitationally tangle. This relative solitude has let our spiral structure stay stable for eons. When it comes to chemistry, our galaxy sits comfortably typical for spirals of similar size and age. Our star's heavy metals suggest we've hit standard rates of star-making and stellar recycling over cosmic ages. Although our sun's metallicity is a bit richer than average, it reflects conditions common in many other spiral galaxies. Fascinatingly, our galaxy is churning out stars at a pace similar to other spirals in this era. We're part of what astronomers dub the Green Valley in galaxy color magnitude space, meaning our star-making rate is winding down as we use up our gas reserves. Such comparisons highlight both our cosmic significance and insignificance. While our galaxy boasts hundreds of billions of stars stretching over hundreds of thousands of light years, it's simply a typical galactic blueprint repeated throughout the observable universe. The presence of 2 trillion other galaxies sparks profound musings on life's likelihood elsewhere in the cosmos. Our galaxy doesn't just float aimlessly, it follows one of the grandest paths ever known. The cosmic web is the universe's ultimate master plan, a vast network of dark matter filaments linking galaxy clusters over billions of light years. These unseen highways shape the way matter and energy flow on mind-boggling scales, sketching a web that covers the observable universe. Nestled in one of these cosmic web threads, our galaxy drifts along a course determined by the gravitational pull of dark matter concentrations formed way back in the universe's early days. Like a train on invisible tracks, we journey through space, steered by forces that dwarf even our massive galactic home. The cosmic web's filaments form the universe's backbone, holding about 60% of its matter. These filaments reach across space, connecting colossal nodes where thousands of galaxies cluster, creating a network similar to a vast cosmic neural network. Huge empty voids, almost devoid of matter, lie between these filaments like the gaps between neurons. Computer models show this intricate web came about naturally from tiny bumps in the early universe. Over billions of years, Gravity exaggerated these initial differences, guiding matter along certain routes and shaping the filaments we see today. Galaxies took form at junctions and along these dark matter paths. Our galaxy group, including the Milky Way and Andromeda, travels along a filament stretching towards the Virgo cluster, a massive collection of over 1,300 galaxies located around 54 million light-years away. This filament provides the gravitational pull that directs our movement through space, linking us to the larger cosmic framework. Inside this filament are not only galaxies, but also large amounts of hot ionized gas, filling the spaces between our galactic neighbors. This gas, heated to millions of degrees, glows softly in X-rays and offers the raw materials needed for future galaxy creation and expansion. Recent breakthroughs have allowed scientists to map the cosmic web directly by spotting this hot gas and measuring the faint gravitational lensing effects caused by dark matter filaments. These findings affirm that our galaxy indeed moves along one of the universe's main structural lines. The cosmic web also influences our galaxy's growth by controlling how matter moves between galactic and intergalactic realms. Gas flowing into our galaxy along the filament acts as fuel for ongoing star creation, while galactic winds propelled by supernovas and stellar radiation may escape along these same routes. This cosmic setting highlights how our galaxy's story and destiny are deeply tied to the vast cosmic scale. If we could somehow zoom out of our galaxy and take a look back, we'd see one of the universe's most gorgeous sights. Our cosmic home would appear as a graceful spiral galaxy, with its sweeping arms glistening from the light of billions of stars arranged in elegant spirals extending from a bright central core. Clusters of bright young stars would light up the spiral arms like twinkling holiday lights strung along cosmic roads, while the older stars' gentle yellow light would softly illuminate the space between the arms. The central bar-shaped structure would span our galaxy's center, with its dense collection of ancient stars revolving slowly around the massive black hole at its core. Dark dust lanes would outline the spiral arms, casting intricate patterns of light and shadow, revealing the galaxy's internal framework and ongoing star formation. From this impossible viewpoint, we could spot the faint halo of globular clusters surrounding our galaxy like glowing insects circling a bonfire. These ancient clusters would appear as tiny concentrated lights, with their orbits outlining our galactic home's true three-dimensional form. The extended dark matter halo would stay invisible, known only through its gravitational effects on nearby stars. The galactic disk would look surprisingly flat when viewed from the side, akin to a cosmic pancake less than 1/50th of its width. The galactic warp would be clear from this angle, showing our galaxy's outer parts twisting up and down like a warped vinyl spinning slowly in space. The satellite galaxies would be visible as smaller companions orbiting our galactic giant. Streams of stars, ripped from these disrupted neighbors, would arc across the sky, marking the gravitational turmoil caused by our galaxy's tidal forces. The approaching Andromeda galaxy would stand out in the distance, its spiral shape distinct against the cosmic landscape. Yet, this external perspective is one we will never experience. We're stuck in our galaxy like living our whole lives in a massive cathedral, able to look at each detail up close but never getting to stand back and see the whole structure. This is how it feels being human when we look at the universe. We exist in a place that's way bigger than us, but we can't really grasp its full beauty or complexity because we're stuck inside it. Instead, we gather bits and pieces of what our galaxy looks like, kind of like archaeologists trying to rebuild an ancient temple from random stones. Even with these hurdles, we've done a great job mapping out our galaxy. Through thorough observations, computer models, and comparing other galaxies, we've found out we live in one of the universe's most stunning formations. Our galaxy stretches over 100,000 light years, has 400 billion stars, and takes part in an incredible cosmic ballet. We're citizens of infinity, living in a cosmic city that's beyond what we can fully understand, always trying to figure out where we fit in the vast cosmic design.